Good evening, all. Welcome to today's live discussion session for the NPTEL course Water Supply Engineering. I am Reshma R, PMRF Research Scholar from Hydraulics and Water Resources Engineering Division, Department of Civil Engineering, IIT Madras. Let me share the screen. Hope it is visible.
Yes, it is visible.
Okay. Okay, so let's start with the session. So here is our question one. The water lost from a water distribution network due to mismanagement of assets and resources rather than real leaks is denoted as option A, apparent losses, option B, non physical losses, option C, commercial losses, option D, all of the above. So, the water lost due to mismanagement of assets and resources can be considered as which type of loss? Is it apparent, non physical, commercial, or is it all of these? Okay, yes. So the answer is all of the above. That is, the water lost due to mismanagement of resources is termed as apparent loss or non physical losses, management loss, or commercial losses. So, here what happens is there is no physical loss of water, but that loss is considered as a loss in utility records. It is actually due to the mismanagement, but still it is considered as a loss in the utility records. So this happens mainly due to the recording or handling, data handling error, sometimes metering inaccuracy, theft of water, or other unauthorized consumption. All these can lead to apparent or non-physical losses. Right. So, moving on to the next question. Question number two. Seepage through reservoir or tank walls and overflow due to float valves failure are accounted for as option A, real losses or physical losses, option B, management losses, option C, commercial losses, and option D, none of the above. So the seepage through a reservoir or tank walls or overflow due to float valves. Which type of losses these kind of losses? Yes, so it's option A, real losses or physical losses. So the amount of water that is physically lost, that is termed as physical loss or real loss. So this mainly happens through a leakage or an overflow. For example, leakage in the pipe, in the joint, fittings, connections, or a seepage loss through the reservoir or a tank wall. Also, overflow due to valves. All these contribute to real loss or physical loss of water. So, the major factors that influence the real loss are first one is the percentage of time in a year during which the pipe is pressurized or the system is pressurized. Another factor is when the system is pressurized, what is the average operating pressure? Third one is the total number of connections as well as the customer meter or consumer meter locations. Then the number of joints, valves, gauges, all the other appurtenances, etc. And the length of the mains, that is the length of the main pipes, and infrastructure condition, that is basically the type of pipe we have used, how old is that pipe. So depending upon that, there can be some what is called as corrosion that is happening, or there can be some deposits along the pipeline. So the age matters, also the frequency of leaks and burst, and the last factor is the type of soil and ground conditions. So all these factors contribute to the real loss. All these factors influence the real loss. Now moving on to the third question. Which of the following statements are true regarding real water loss from distribution networks? Statement 1. In a typical water utility, UFW is a component of NRW. Statement 2. Billed unmetered consumption is not a component of NRW. Statement 3. ILI of a utility can be estimated if either its UFW or NRW is known. Option A. All statements are true. Option B. Statement 3 only. Option C. Statements 1 and 3. Option D. Statements 1 and 2. So, which of these are true? Okay, so we'll see the answer. The correct answer is option D, that is statement 1 and 2. So, UFW is actually a component of NRW. So, UFW is nothing but unaccounted for water, and NRW is non revenue water. So, this non revenue water is actually UFW plus unbilled authorized consumption. Billed unmetered consumption is not a component. Only the authorized consumption is the component of NRW. Billed unmetered consumption is not a component. But it is considers a component of authorized consumption. So unbilled authorized consumption only it considers. It doesn't consider billed consumptions. Like billed unmetered consumption is not a component of NRW. So statement 2 is correct. Statement 2 is correct. Now, ILI of a utility cannot be estimated from UFW and NRW, but it depends upon pipe length, average operating pressure, as well as the physical losses in the system. All right. So we'll see what is happening actually. This image shows the water losses and non-revenue water. So we can see that once the water is supplied, there can be different types of water losses. There can be authorized consumption, that is those who have got the connection in a proper manner through municipalities and other supply distribution systems. There can be real loss as well as apparent losses. And in the authorized consumption, there can be unbilled and billed authorized consumption. Again, unbilled authorized consumption is not acceptable. So, this losses along with unbilled authorized consumption comes under non-revenue water, whereas billed authorized consumption gives you a revenue. So, it is revenue water that gives the authority a revenue. So, it comes under revenue water. So, non revenue water or NRW is thus the volume of water for which there is no revenue generation. So, it can be either the loss or it can be unbilled consumption, unbilled authorized consumption. So, it is the system input volume minus billed authorized consumption that constitute NRW. Right. So UFW or unaccounted for water, on the other hand, is the difference between net production and legitimate consumption, whether metered or not. So it's equal to system input volume minus authorized consumption. So it's actually an estimate of total water loss. It includes real loss as well as apparent loss. That is physical as well as non-physical losses included in unaccounted for water. Okay. So here we can see that the water loss indices, we can see that UFW is equal to SIV, that is system input volume, minus BAC, built authorized consumption, minus UAC, that is unbilled authorized consumption. So that constitutes the real loss plus apparent loss, or which together is known as unaccounted for water, UFW. So if we have to represent this as a percentage, it becomes UFW in percentage is equal to SIV, that is system input volume, minus billed authorized consumption minus unbilled authorized consumption, the whole divided by system input volume into 100. Sorry. So that is the unaccounted for water expressed in percentage. Coming to non-revenue water, it is, as we saw, it is the difference between system input volume and billed authorized consumption. Or it is like this first part from UFW, right? So it is UFW plus UAC. That means it is real loss plus apparent loss plus unbilled authorized consumption. Again, NRW expressed as percentage is given by SIV, that is system input volume, minus billed authorized consumption, the whole by system input volume into 100. Okay. Okay. So moving on to the next question. The real losses in a water distribution network usually increase with option A, decrease in the number of consumer or service connections, decrease in the number of joints, valves, and gauges. Option C, increase in the average operating pressure of the system. Option D, all of the above. So, how, like, with what does actually the real loss increase? You can type in your answers in the chat box. Okay, so the correct option is option C, that is increase in the average operating pressure of the system. So the real losses in a water distribution network usually increases with increase in the average operating pressure in the network and the duration for which the network is pressurized. Also, it increases with increase in consumer connections, service connections, as well as with increase in number of joint, valve, other appurtenances, etc. Okay. Question number 5. Unauthorized consumption plus metering and billing inaccuracies in a water distribution network equal to. So, what is unauthorized consumption plus metering and billing inaccuracy? Option A, real losses. Option B, non revenue water. Option C, unaccounted for water. Option D, apparent loss. So, just now we saw the definition for all these. So, what is unauthorized consumption plus metering and billing inaccuracy? Is it real loss, non revenue water, unaccounted for water, or apparent loss? Okay, the correct answer is option B, apparent losses. As we saw earlier, apparent losses consists of input, output, and customer metering inaccuracy. All the mismanagement comes and losses due to mismanagement comes under apparent losses, and all type of unauthorized consumption, that is including theft and illegal connections, comes under apparent losses. So now question number 6. The core component of non-revenue water is option A, unbilled authorized consumption, option B, real losses, option C, apparent losses, option D, all of the above. So, which is the core component of non-revenue water? Okay, so the correct answer is all of the above. That is, non-revenue water is equal to unbilled authorized consumption plus real losses plus apparent losses, as we saw in the earlier slide. Okay. Question number 7. Which of these methods can assess the volume of leakage in a water distribution network without pinpointing its location? Option A, ground microphone. Option B, minimum night flow analysis. Option C, tracer gas technique. Option D, none of the above. So, which can assess the leakage without pinpointing the location? Yes, the correct option is option B, minimum night flow analysis. So, minimum night flow is the lowest flow into a DMA over a 24-hour period. Normally, that occurs between 2 to 4 a.m. when most users don't use water. So, this is a minimum flow time. So, that usually happens in the early morning 2 to 4 a.m. period because most of the consumers are not using water during that time. So, the water flow during this time is actually considered predominantly leaks, and that helps in estimating real loss. But what happens here? Whatever night flow happens in that time interval is considered as leaks or leakages. But we don't know whether it is really a leakage or whether it is someone is using it. And the another problem is that it will not pinpoint the location where the leakage is happening. It just gives a estimation of the value. So estimation of leakage is equal to minimum night flow minus legitimate night flow. Now what is legitimate night flow? It is roughly calculated as 6% population using 10 liters of water for toilet flush. So that is like some amount of water will be definitely used by some people here or there. So to take into account that consumption, estimation of leakage through minimum night flow is done as minimum night flow minus legitimate night flow. And this legitimate night flow is taken as assuming that 6% population will roughly use a 10 liter of water for toilet flushing. Okay. So question number 8. Which of the following statements concerning acoustic methods of leak detection is or are true? Option A. The efficacy of leak noise loggers in pinpointing exact leak locations can be increased by using them in combination with correlators. Option B. The leak noise correlator pinpoints the leak location using only the distance between the two sensors. Option C, both A and B. Option D, none of the above. So, which statement is true? So, it's option A, B, or both A and B, or none of them. Okay, so the correct answer is option A. That is, the efficacy of leak noise loggers in pinpointing exact leak locations can be increased by using them in combination with correlators. So that's a true statement. So leak noise loggers can identify leaks immediately as they occur but does not identify the exact location without the use of correlator. Only if we use them combined with a correlator, we can get an exact location pinpointed. So the leak location from the sensor is given as d minus c delta t by 2, where d is the distance between sensors, c is the propagation velocity of sound, and delta t is the time lag corresponding to difference in arrival times of leak signals. All right. So moving on to the next question, question number 9. Which of the following is a remote mode of leak detection and quantification? Option A, tracer gas technique. Option B, ground penetrating radar technique. Option C, smart ball technique. Option D, all of the above. So, which is the remote mode, remote method? Yes, correct answer is option B, that is ground penetrating radar technique. So, the ground penetrating radar technology or GPR technology, it utilizes electromagnetic waves that lies between 125 and 370 megahertz. They transmit these electromagnetic waves once into the ground to identify the leak location using imaging the subterranean, including the pipe and leak. So, it's a remote method. So, unlike the option A and C, where the smart ball and tracer gas techniques are there, this ground penetrating radar can operate remotely from a distance. Okay. So, we'll see what are the details of water loss detection. So, leakage or loss detection is actually a critical parameter when we come to water distribution networks, because if there are more unauthorized consumption, if there are more theft of water or leakages happening, what will happen is a huge loss of water or a good percentage of water from the supplied water. And that too, if leakages happen, it can cause problems in the normal distribution of water, as well as it can cause water logging issues wherever the leakage is happening. So the leak detection is a critical parameter. So the process is like, first we need to detect the leak, then we need to quantify it, and then we need to pinpoint the location. That is leak detection, leak quantification, and leak localization. So in leak detection, the presence of one or more leaks is identified. In leak quantification, the severity is assessed, the magnitude is assessed. And in leak localization, what we do is the exact location of leak is identified. So the process is like first we need to detect, then quantify, and then localize. So these are the different leak detection methods according to Zaman et al. That is available now. So there are direct methods as well as indirect methods. In direct methods, we have hardware based methods, visual inspection, and pipe sampling. In the hardware based methods, it's like robotic devices or out of pipe devices. So these are new technologies that have come in. The most obsolete method among this direct, indirect, and inferential method is the inferential method, that is most obsolete, where we do soil monitoring, soil LPR, or pipe soil potential surveys. Okay. So we'll see some of these methods in detail. The first one is minimum night flow analysis that we saw earlier. So as we saw, it is the lowest flow happening over a 24-hour period, that too during 2 a.m. to 4 a.m. So this the assumption is that during that time period the flow is mostly due to leakages that is happening, and if some consumption is happening, that is considered as legitimate night flow, which is subtracted from minimum night flow to obtain the leakage value. That is, real loss is equal to minimum night flow minus legitimate night flow. So the estimation through this method is usually not valid because it usually overestimates for the daytime, as the average operating pressure during day is less. So according to Lambert, the pressure leak relationship is expressed as L1 by L0 is equal to P1 by P0 raised to n, where L represents leakage, P represents pressure, and N represents leakage component or leakage exponent that varies from zero point 0.5 to 1.5. That is, for a connection with fixed area leakage path, then it is zero point 0.5. If the leakage path is variable, we should take N as 1.5. Okay. The next method is step testing. Next method of detecting leakage is step testing. This is based on systematically reducing the network size. So what happens here is, one by one, the valves are closed in the considered section of the pipe, and then the flow monitoring is done. For example, if we just close the pipe and if we see a large decrease in the flow rate, we can be sure that the leakage was happening in that closed pipe section. So this is designed by identifying test area and section of pipe network. So traditional approach that we take in the municipality level or water supply level is that we'll shut off valves step by step from the consumer end to the meters, and once the test is over we'll reopen all the valves. But the problem with this method is this is not much accepted by the consumers, since there can be severe interruptions in the supply. So what they have come up is with an alternative where we use a series of short steps. That is, very for a very short time only the valves will be closed, so that much interruption won't come in the supply or regular supply of water. So this actually requires a remote meter reading device positioned at the meter for transmitting flow rates, so that we can immediately see the results of the valve closure. The next method is using the acoustics sound. So acoustic leak detection. So When water leakage happens underground, the pressurized pipe may make different types of sounds. For example, hiss, whoosh, splashing, babbling brook, beating, thumping, clinking, all these different kinds of sounds will be made when water leakage happens underground. So, the hiss or whoosh sound is from pipe vibration and orifice pressure reduction. Splashing from water flowing around the pipe. Beating from water spray striking the wall of soil cavity. Clinking, that is sound of stone and pebble bouncing off the pipe. So depending upon the sound generated, we can identify the condition out there underground. So the loudness and frequency is a function of pressure in the pipe material and diameter, soil type and surface cover, compaction level, and depth of pipe from the surface. So here what we do is we'll transmit the sound through the pipe as well as through ground. Then using acoustic sensors, we'll identify the nature of sound and frequency with which it is generated. So sound travels faster or better in pipe walls rather than the soil. So we usually use sensors at hydrant, valve, and meters, and then only we go for ground sensors. Ground sensor is for pinpointing the location. So the rough estimation is done by the sensor in the hydrant or valve. So this is what happens there. So this can be done either in contact mode or survey mode or both. On fittings, we can do contact mode. Between fittings, we can go for survey mode. So with the deflection in the meter, whether it is weak, loud noise that is coming, we will detect the location and leakage quantities. So the next one is leak noise loggers. That is a microphone plus a logger. So that is installed on a group of adjacent fittings. This will be a semi permanent or permanent monitoring system will be there. So they actually, one or more of the fittings they will identify, like they will consider the characteristics between similar fittings, and then they will search on the unique features coming out due to the leakages. But the problem is again, this cannot pinpoint the location where it has happened, sorry, and it has a high initial cost also, because this real time monitoring system needs, it's bit costly. The next one is sounding surveys. So this is like listening devices are used in order to analyze the sound that is being generated in the appurtenances along the pipe network. These are highly accurate and sensitive. So these are carried out using various types of equipments. For example, acoustic listening stick, electronic listening stick, ground microphone, leak noise correlators. All these are used for sounding surveys. So that is leak noise correlator that is here. So this is a portable instrument. This actually depends upon the velocity of sound that is produced due to the leakage. So the velocity as it propagates along the pipe wall, it will collect, and the largest of the core versions of correlator can actually give up to 1 meter accuracy in the leak location. Another is leak positioning. So if we have to identify the exact position, the time lag is to be calculated, and that is given by, that is difference between the arrival times in measured signals, and the time lag, as we saw earlier, it is L2 minus L1 by C. So from this equation we saw, that is leak location is equal to D minus C delta T by 2. So this will give the leak location or leak positioning. So this distance is from the sensor to the leakage point. Okay. The next method is tracer gas injection for leak detection. So these are like, uh, here what we do is we'll inject a tracer which is inert, non-toxic, insoluble gas. This we will introduce into the pipe network. For example, using a hydrant, and the gas, since it is lighter, they will try to escape through the leaks as shown in the picture. So this particular leakage of gas is detected using microsensors, and this is usually used for all type of materials. Like it can be used for all type of materials, but usually not used just because of the additional cost that comes in here, high cost. So we do not recommend it for larger pipelines. And the major application is like, to identify the small background leaks or leaks in service pipes, etc. Some other methods are like infrared thermography, ground penetrating radar, leak detecting robots, wireless micro electrical electromechanical devices, data sensing and analysis based software, etc. So ground penetrating radar we saw earlier, it is a remote method. Infrared thermography is like, it uses infrared or IR images capturing the emitted infrared radiation and then detecting thermal contrast that occurs due to water leak. So these days we have leak detecting robots as well. For example, smart ball is there, where they do pipe inspection and the leak location. Also we can have micro electromechanical devices where we have micro sensors and actuators for leak detection and repair. And there are various software and or artificial intelligence AI based technologies that is getting developed these days. All right. So moving on to the next question. An urban water utility pumps an average of 600 million liters per day of treated water into its water distribution network. The utility records an authorized consumption of 525 million liters per day through its bulk meters, but collects revenue from the billed metered connections only for 475 MLD. Determine the approximate values of NRW and UFW in percentage of the utility per day respectively. Option A, NRW is equal to UFW is equal to 13 percentage. Option B, NRW is equal to UFW is equal to 21 percentage. Option C, NRW is equal to 13 percentage. UFW is equal to 21 percentage. Option D, NRW equal to 21 percentage, UFW is equal to 13 percentage. So please calculate and put the answer in the chat box. Okay, so the correct answer is yes, um, option B. That is NRW is equal to 21 percentage and UFW is equal to 13 percentage. Yes. So we are given with the average treated water pumped, that is equal to 600 million liters per day, and authorized consumption recorded as 525 million liters per day. So the consumption for which revenue is collected is 475 million liters per day. So we need to determine NRW and UFW. So we know that unaccounted for water, we earlier saw the equation is system input volume minus total authorized consumption. That is 600 minus 525, which is equal to 75 million liters per day. Now we need this in percentage. So dividing it by system input volume and multiplying it with 100, we have UFW is approximately equal to 13 percentage. Now coming to NRW, it is equal to system input volume minus billed authorized consumption. Sorry, it's unbilled authorized sorry, it's correct. System input volume minus billed authorized consumption. So that we'll get the unbilled consumption. Yes. So NRW is equal to 600 minus yeah 475. So that is 125 million liters per day. So coming like taking it into percentage, that is dividing by system input volume, we have NRW in percentage is equal to 21 percentage approximately. I hope that is clear. So we have the next question. It's a numerical problem. The leak flow rate in the water transmission line under 3 bar pressure is estimated to be around 12 meter cube per hour. Determine the leak flow rate in meter cube per hour in the transmission line if the pressure is increased to 4.5 bar pressure, assuming a fixed area leakage path and using leak pressure relationship proposed by Lambert. So we saw that equation earlier. Please solve the problem using that and type in the value in the chat box. So it's direct substitution in the equation given by Lambert. Okay, I have got two values, like two numbers I have got. We'll see. Correct answer is 14.7 meter cube per hour. So we are given that the leak flow rate under 3 bar pressure is 12 meter cube per hour and the final pressure is 4.5 bar. So according to the equation we have L1 by L0 is equal to P1 by P0 the whole raised to n. So L0 P0 is given, P1 is also given, L1 is unknown. So as we saw earlier, n lies between zero point 0.5 to 1.5. So if it is a fixed leakage path, it is zero point 0.5, and for variable it is 1.5. So here it is zero point 0.5. Substituting the values, we have L1 is equal to 14.7 meter cube per hour. So the next question, the apparent loss estimated from a faulty bulk meter in the water supply in a residential complex is 15 kiloliter per day. Determine the inaccurate reading of the faulty bulk meter corresponding to the actual water flow of 1 kiloliters if it records 4500 kiloliters of cumulative monthly flow. So try to solve this. Okay, so we'll see how to solve the problem. So the correct answer is 0.91 kiloliters. So we are given that the parent loss estimated from faulty bulk meter is 15 kiloliter per day and actual flow is 1 kiloliters. Cumulative monthly flow recorded is 4500 kiloliters. So the apparent loss per month will be 15 into 30. For 30 days they have told to calculate. So that is 450 kiloliters. So actual flow is apparent loss plus meter display. That is 450 plus 4500. That means 4950 kiloliters. So this 4950 actual flow is read as 4500 in the bulk, faulty meter. Right. So 1 kiloliter will be read as 4500 by 4950, which is 0.91 kiloliters. Hope that is clear. Now we have a problem statement for 13 to 15 questions. A newly built water distribution network with 19795 service connections, 1267 kilometer of pipe main, and 5035 kilometer of underground service pipes from property line to water meters delivers 120 million liter per day water to a city. So question number 13, if the utility desires the unavoidable annual real losses, that is UARL, to be 3% of the supplied volume, determine the volume of water lost per year. So I'll show you the statistics once again. Please note it down. Please note down the value so that you can do the calculation. I'll give you 1 minute or 2 minutes maybe. Okay, I hope you have noted the values down. So this is the question. Please try to solve it. Okay, so I've got two answers. That is correct only. Yes, 1314 million liters per year. So we are given with number of service connections, length of pipe mains, length of underground service pipes, and amount of water being delivered. So it's given that UARL is to be considered as 3 percentage. That is 3 by 100 into 120, that is amount of total water being delivered over the year. So 0.03 into 120 into 365, which will give you 1314 million liters per year. So coming to second question, that is determine the average pressure required to be maintained in the distribution network to ensure a UARL of 3 percentage of the supply volume. So if we have to ensure that this UARL will be 3 percentage, what is the average pressure to be maintained? So all the other data remains the same. Here we need to determine the average pressure required. So please try to solve it. Okay, so we'll see how to solve this. So the correct answer is 21.9. So the number of service connections, length of pipe mains, like length of underground service pipes, and amount of water being delivered, all these values were given in the earlier question itself. And UARL, we had calculated it as 1,314 million liters per year. So that is converted into meter cube per year here. Now, in order to maintain this UARL as 3 percentage, or to ensure that the pressure required is obtained from this particular equation, that is UARL is equal to 6.57 Lm plus 0.292 Ns plus 9.132 Lp, the whole into P. So here all the other values except the pressure is known. and hence by resubstituting for P, we have P is equal to 21.9 meters. Now question 15. If the real loss from the system after 1 year of operation is estimated as 2076 million liter per year, determine the ILI of the distribution network. So all the other data remains the same as in the previous question. So please try to solve this. Okay, so we'll see how to solve this. Yes, the correct answer is 1.58. So we are given that the current annual real loss CARL is 2076 million liter per year, and the unavoidable annual real loss we have calculated already as 1314 million liter per year. Now, infrastructure leakage index or ILI is given by CARL divided by UARL. That is, ILI is equal to 2076 by 1314, which is 1.58. Okay, so the current annual real loss is nothing but the real loss estimation, and unavoidable annual real loss is the almost impossible to eliminate the, like, some amount, the amount that is almost impossible to eliminate, that amount is unavoidable annual real loss. Somehow it is always unavoidable. So that is given by a particular equation, and the infrastructure leakage index is then the ratio of these two. I mean, CARL and UARL. Okay. So the ideal value will always be 1. The ideal value of ILI will be always 1. Now coming into the last question, that's the 16th question. So this is, last time we had missed one question because of a missing parameter. So here we have another similar question. Determine the equivalent diameter in mm of a 900-meter long equivalent new pipe for a piping system consisting of three pipes connected in series. The length of the individual pipes is 200 meter, 300 meter, and 400 meter respectively, and their individual diameters are 200 mm, 150 mm, and 250 mm respectively. So please try to solve this question. Determine the equivalent diameter. So we'll see how to solve the problem. So the correct answer is 178.4 mm. So we are given that length of individual pipes is 200 meter, 300 meter, and 400 meter, and their diameters are 200, 150, and 250 mm respectively. So when the pipes are in series, head loss will be sum of the head loss in each of them, and discharge will be equal in all when the pipes are connected in series. That is, H equivalent is equal to H1 plus H2 plus H3, and Q equivalent is equal to Q1 is equal to Q2 equal to Q3. So, considering the Darcy-Weisbach equation and then supplying that in the head loss equation where H equivalent is equal to H1 plus H2 plus H3, and resubstituting in Q, we will get this form, that is L equivalent by D equivalent raised to 5 is equal to L1 by D1 raised to 5 plus L2 by D2 raised to 5 plus L3 by D3 raised to 5. All other terms will get cancelled. So here only unknown is D equivalent. Substituting all other values, D equivalent can be solved as 178.37 mm. Hope that is clear.
Yes.
Okay. So With this, we come to an end for the today's discussion slides. So if you have any other doubts, we can discuss that, or else I shall stop my presentation here. Okay, so it's like, oh, sorry. Yeah. So it's like we have completed today's session. So if any further doubt is there, we can discuss that, or else we can close the session and we'll meet again during next discussion session on next Tuesday. Okay. Thank you all.